Human beings figure out what's going on in the world around them by seeing, hearing, smelling, touching, or tasting. The computers in our vehicles also need to know what's going on around them. They get their information electronically. Today, we're going to talk about the basics of engine sensors. We'll begin by examining how automotive computers receive and process information. Then we'll look at the basic operating principles of sensing devices. Next, we'll examine two sensors in detail, the Manifold absolute pressure sensor and the coolant temperature sensor. And finally, we'll finish up with a quick summary to review what we've covered. The current generation controller is called a powertrain control module, or PCM. It controls a variety of functions, including fuel metering, transaxle shifting, cruise control operation, ignition timing, and others. But before it can control anything, the PCM itself must have a good voltage supply and a proper ground. The PCM is a computer. Like any computer, it works in a three-step process. Step 1. It accepts information. Step 2, it analyzes that information and makes a decision. Step 3, it issues a command signal. Sensors provide information called input. Input tells the PCM about atmospheric conditions and operating conditions. Atmospheric conditions are air temperature and barometric pressure. Operating conditions include oxygen content in the exhaust, engine coolant temperature, throttle position, manifold absolute pressure, mass airflow, and so on. Sensor input signals go to the PCM's memcal, which the controller uses to make decisions and issue appropriate command signals. Several types of inputs are available from a variety of sensors. One important distinction is whether a signal is digital or analog. The word digital means having to do with numbers. It refers to the fact that this kind of signal has only two states, high voltage and low voltage. A computer interprets high voltage as the number 1 and low voltage as the number 0. Unlike digital signals, analog signals represent a continuously variable voltage. This signal can be high, low, or anything in between. Since the microprocessor works with digital information, it can accept digital signals directly, but it can't do that with analog signals. The PCM must first process them through an analog to digital or A to D converter. The PCM monitors all sensor signals, analog and digital, as voltage. To do that, it uses a voltage monitoring circuit, which you can think of as a built-in voltmeter. Section 8A schematics always show sensor inputs with this internal resistor. It has several functions, but for our purposes, it's enough to know that the PCM's built-in voltmeter measures the voltage drop produced across this resistor by the input from the sensor. The simplest type of sensor is a switch. Because it generates either high voltage or low voltage, its signal is digital. The AC request input uses two switch sensors connected in line, the AC high pressure cutout switch and the compressor cycling switch. With either switch open, no voltage reaches the input, and the PCM sees low volts or digital state 0. With both switches closed, the full supply voltage is dropped across the internal resistor. Now the PCM sees high volts or digital state 1. This is how it knows when the climate control system is asking for AC compressor operation. In the circuit we've been examining, the PCM supplies ground for measuring the input voltage. For many other sensors, the PCM provides a reference voltage instead of ground. The transaxle position, or Prindle switch, is one such sensor. Here, the PCM supplies 5 volts to the circuit. When all the switches are open, no current can flow through the sensor's circuit. With no volts being dropped across the internal resistor, the built-in voltmeter reads the full 5-volt reference voltage. When any switch closes, current flows through the circuit. Now the reference voltage is dropped across the resistor, and the built-in voltmeter sees about 0 volts. Another type of sensor uses a variable resistance instead of a switch. This example shows a potentiometer. Notice that it has 3 terminals. One terminal is connected to voltage, another to ground. The potentiometer's wiper is connected to the 3rd terminal, which is the sensor's output signal. The sensor's output voltage depends on the position of the wiper. Because this voltage is continuously variable, the output is an analog signal. The throttle position sensor uses this principle to generate its signal. The coolant temperature sensor uses a similar circuit, but instead of a potentiometer, this one uses a thermistor. That's a device which changes its internal resistance in response to temperature. As the resistance of the thermistor changes, the voltage drop across the sensor and the voltage appearing at the sensor's input change with it. Finally, there is a type of input that uses a pulsed or toggled voltage. This is a digital signal which incorporates the added element of time. In addition to monitoring high and low voltage, the PCM also counts how many pulses occur in a specified time interval. You can think of this type of sensor as a switch that can open and close rapidly, many times per second. To read such inputs, the PCM uses its internal voltmeter, internal resistor, and an internal timer. Applications for frequency-modulated inputs include ignition reference pulses and vehicle speed, oxygen, crankshaft, and camshaft sensors. If you'd like more information about crankshaft sensors, camshaft sensors, and ignition reference inputs, please review the Distributorless Ignition System Service Alert release. And if you want a more detailed review of basic sensor circuits, take a look at Electronic Diagnosis 3. The manifold absolute pressure, or MAP sensor, converts pressure readings into voltage signals. It does that using an electronic device called a strain gauge. A strain gauge is constructed using a very thin silicone chip and a small piece of glass with a cavity machined into its surface. The chip is placed over the cavity, and its edges are sealed so that it traps a bubble of air. That assembly is then put into a sealed housing, which is connected to manifold absolute pressure through a small tube. If you look at a cross-section view of the glass and the silicone chip, you can see that the air trapped beneath the chip exerts pressure from below, and air piped in from the manifold exerts pressure from above. When the chip is first sealed to the glass, air pressure is controlled to exactly 1 atmosphere, which is equal to 14.7 psi, or roughly 30 inches of mercury. With the vehicle at sea level and the engine not running, pressure in the manifold should be exactly 1 atmosphere. That means air pressure above the chip would be exactly balanced with the air trapped below the chip, both exerting 14.7 psi. If you started the engine, manifold absolute pressure would go to something less than 1 atmosphere, which we usually call vacuum. This would cause the pressures on the chip to be unequal, with the trapped air exerting more pressure than the manifold air. This unequal pressure causes the chip to flex slightly outward. On engines with forced induction, you could also raise manifold pressure above 1 atmosphere. In that case, the chip would flex slightly inward. As the chip flexes, its internal resistance changes. As the sensor's resistance changes, the PCM monitors the resulting changes in the voltage drop across its internal resistor. For EFI and PFI systems, MAP sensor output voltage should be about 4.8 volts with the vehicle at sea level, ignition on, and the engine not running. With the engine running, the signal voltage ranges from 1 to 1.5 volts at idle to 4 to 4.5 volts at wide open throttle. The PCM monitors these signal voltages many times per second. Each time it gets a voltage, it checks that value against a lookup table. That's a set of values stored in the PCM's read-only memory, or ROM. Using this table, the PCM calculates the load on the engine. The PCM then factors engine load into its calculations for fuel delivery, ignition timing, and torque converter clutch operation. In some fuel-injected systems, the MAP sensor does double duty as a barometric pressure or barosensor. The sensor can do this because manifold pressure is equal to barometric pressure under two conditions. One, with the ignition on and the engine not running. Two, with the engine running and the throttle wide open. The barometric pressure reading is just as important as the manifold absolute pressure readings are. The PCM uses the baro reading to calibrate the values it sees when the engine is running. So if the barometric reading is inaccurate, it throws off the PCM's fuel delivery and ignition timing calculations. The effects can be severe enough to cause an engine performance problem, yet this condition would not cause the PCM to set a trouble code. Of course, there are conditions that do cause the PCM to set MAP-related trouble codes. The PCM sets a code 33 whenever it detects all of the following conditions at the same time. Engine is running, throttle opening is less than 4%, and MAP sensor output is too high for longer than 5 seconds. It's also possible for the PCM to set this code when there's an engine misfire or a low or unstable idle. If you have a misfire or bad idle condition, try disconnecting the MAP sensor. With the sensor disconnected, the PCM uses a default MAP value and controls fuel delivery based mainly on TPS signals and engine RPM. If disconnecting the sensor makes the engine run better, troubleshoot the sensor. If it doesn't, troubleshoot the misfire or idle condition. The PCM will set a code 34 when it detects the following conditions at the same time. Engine is running at less than 1200 RPM and MAP signal voltage is too low. Or the engine is running at more than 1200 RPM, throttle opening is more than 21%, and MAP signal voltage is too low. Let's summarize what can happen because of MAP sensor problems. If MAP signal voltage is too low, the PCM cannot properly detect high engine loads. Without enough fuel, the engine would stumble and surge. Also, improper ignition timing could cause detonation. If MAP signal voltage is too high, the PCM behaves as if there is a high load on the engine. With too much fuel being supplied, the engine would run rich. Also, the system would provide less than the ideal ignition timing advance. The coolant temperature sensor, or CTS, converts temperature into voltage signals. It does that with an electronic device called a thermistor. The sensor body is installed with its probe immersed in engine coolant. As coolant temperature changes, the thermistor responds by changing its electrical resistance. The type of thermistor used in coolant temperature sensors has a negative temperature coefficient. Don't let that term scare you. It's just a fancy way of saying it has high resistance when it's cold and low resistance when it's hot. Thermistor resistance ranges from over 100,000 ohms at minus 40 degrees to around 300 ohms at normal engine operating temperature. You can find a table in the Section 6E trouble code diagnostic charts that gives the approximate equivalent values for temperature and resistance. If the engine hasn't been run for at least 5 hours, coolant temperature is probably quite close to ambient air temperature. This gives you an opportunity to compare CTS output, either to an accurate thermometer or to the signal from the intake air temperature sensor. The PCM supplies a 5-volt reference and ground for the CTS. To measure the CTS signal, it monitors the voltage drop produced across an internal resistor. With coolant temperature low, the thermistor's resistance is high. Very little current flows through the thermistor. The PCM's built-in voltmeter reads a value close to the 5-volt supply. Once the engine is running, coolant temperature normally rises steadily until it's about 85 to 95 degrees centigrade. At normal engine operating temperature, the thermistor has substantially reduced its internal resistance. The lower resistance allows a larger current to flow through the thermistor. The PCM's internal voltmeter now sees 1.5 to 2 volts. The PCM uses the CTS signal to control many functions, including fuel delivery, ignition timing, EGR, TCC, and IAC operation, and cooling fan control. In addition, the PCM uses CTS output as part of its decision to run open or closed loop. When the PCM gets an out-of-range signal, it turns on the service engine soon lamp and sets a trouble code, 14 for high temperature, 15 for low. It's also possible for CTS output to be out of calibration enough to cause a performance problem without the PCM setting a code. If the sensor reports that coolant temperature is much lower than it actually is, the system may never go into closed loop mode. Other potential effects include not allowing TCC lockup, overly rich fuel mixture, and improper ignition timing. Let's summarize what we've talked about today. Sensors provide inputs to the PCM. The microprocessor in the PCM analyzes the input to make decisions and issue command signals. Switch-type sensors open or close to prevent or allow current flow. Such sensors provide a digital signal that the PCM sees as high or low voltage. Digital inputs go directly to the PCM's microprocessor. Analog inputs, such as the throttle position, map, and engine coolant temperature signals, are first converted to digital form by an A to D converter. Analog signals are produced by variable resistance type sensors. These include temperature and pressure sensors, which respond to changes in the sensed condition by changing their internal resistance. Analog signals appear to the PCM as a continuously variable voltage. After conversion, the PCM compares these voltage values against information stored in lookup tables. Frequency modulated inputs are digital signals that incorporate the element of time. These signals toggle between high and low voltage many times per second at a variable rate. The PCM monitors how many times each frequency modulated input changes from high to low in a given time period. Frequency modulated inputs include the ignition reference signal and vehicle speed, oxygen, crankshaft, and camshaft sensors. At some inputs, the PCM supplies ground for measuring the voltage signal from the sensor. At others, it supplies a reference voltage, typically 5 volts DC. But no matter how the input circuit is made up, the PCM always gets its information by reading the voltage produced across an internal resistor. As you're troubleshooting, use this basic information, along with the 6E or 8A schematic, to determine how the circuit should work. Keep in mind that these circuits need the correct voltage supply for the sensor, a good path to ground, and of course, a properly working sensor. Also, don't forget the PCM itself must have a good voltage supply and ground. If you're seeing symptoms that seem to involve more than one sensor, be sure to check PCM power and ground. Then, using nothing more than a scan tool and a digital multimeter, you'll be fixing them right the first time. I'm Jim Scopolitis, and I'll see you next time.